With the help of this film sequence, we'll be giving you an overview of the energy solutions that Ericsson provides today. Let's first briefly refresh our memories about the core exchange site power solution.
In Ericsson, a core exchange site could consist of a switch with all its components. One of the important components on a core site like this is the power supply equipment. You will appreciate that no operator can afford to lose a whole telephone network in the event of a power failure. The power equipment must therefore supply the switch with an uninterrupted DC power source. In order to supply uninterrupted power to the switch, there must be some sort of backup system. The backup system could consist of banks of batteries connected together and supplying the necessary DC backup capacity. Batteries, however, have a finite capacity, and if the operator needs to provide a continuous service, then perhaps a diesel or petrol generator may be needed to supply uninterrupted AC to the distribution box. If we take a look at a typical power distribution, we will see the AC input power source at a main switch. This could be situated inside the switch room or in another room in the building. The AC power is divided into branches and distributed to the various equipments, such as our power cabinet. The power cabinet contains rectifiers to convert AC to DC. DC is used in Ericsson switch equipment as well as most other equipment. The DC power is then distributed to the various core equipments. In the event of a main AC power failure, the batteries will continue DC distribution for as long as their capacity lasts. As you see, the principles of Ericsson Power Solutions are quite simple.
So let's now look at each part of the overall telecom power solution in a little more detail. The AC supply to a building is normally a 400-230 volts three-phase AC distribution system. An AC load is any kind of equipment that draws its power from an AC power supply system. An AC load can be connected to the three-phase AC distribution system in different ways. A single-phase load is usually connected to one of the phases, L1, to neutral, N, and probably also to protective earth, PE. The voltage between the phase and the neutral is approximately 230 volts in most countries. That's the most common way of connecting a single-phase rectifier onto 30 volts system. Now just a note here, a single-phase rectifier has its own fuse or circuit breaker for the phase connection. This for operating safety. The biggest rectifiers are connected to all three phases. This gives the best performance for the mains network with less risk for neutral overload, earth currents and so on. This way of connecting rectifiers gives an equal load to all three phases, which is the ideal situation. Note here that a three-phase connection needs three fuses or circuit breakers for operating safety. Normally, these three circuit breakers are connected in parallel with each other. The AC supply has to be made safe for the equipment. So, let's now take a look at what AC protection means and why we apply it. The main function of AC protection is to stabilize the incoming AC and to neutralize short, harmful voltage variations, so-called transients, and prevent them from damaging the power and telecom equipment. The telecom equipment needs to be supplied with a steady voltage without any disturbances. If the AC is of poor quality, it needs to be filtered before it enters the rectifier. If not, there's a risk the rectifiers will break down. This filtering step requires AC filters. The type of AC filter used depends on the degree of risk of mains disturbances and of lightning strikes in a certain environment, as well as the site's physical location and its strategic importance. The number of phases the rectifier type and the number of rectifiers must also be considered. Automatic voltage regulation can be added to smaller filters. After the AC has passed through the AC protection devices, it's usually split up from one large AC cable into a number of smaller AC cables called AC distribution cables. Each one of these smaller AC cables then feeds one or more rectifiers with AC. As a final safety precaution on the AC side, each of these AC distribution cables are connected to an AC distribution circuit breaker, dimensioned to guarantee safe AC supply to the rectifiers. For easy handling, these numerous AC distribution cables are all distributed from a unit that carries the AC distribution circuit breakers. This box is called an AC distribution unit. There's also a way to supervise the AC power using a unit called an AC power supervision unit. This unit measures, analyzes, and controls a wide range of parameters. All parameters and alarms can either be displayed via a central supervision unit or on local PC. If the AC mains should go down for a long period of time, you'll need a backup AC system that can feed the power system. One or several standby diesel generators can be used for this purpose. When the AC mains fails, the diesel engine starts up to supply AC to the rectifiers. The AC that comes from the mains network is then converted to DC. Telecom equipment loads normally operate at a DC supply voltage of -48 or +24 volts. A rectifier converts incoming AC from the mains to DC. The DC from the rectifiers supplies the telecom equipment and charges the batteries. The rectifiers in the power supply plant deliver a constant voltage to the load during normal operation. This constant voltage simultaneously keeps the batteries charged. The number of rectifiers and their size varies depending on the size of the telecom equipment and batteries. That means that the number of rectifiers and their size has to be sufficient to recharge the batteries after mains restoration and at the same time supply the telecom equipment with the power needed. So if the AC mains should go down, a backup that can feed the telecommunication equipment with DC for a short time, let's say a couple of hours, would be needed. The batteries provide the DC backup during the time when the main supply isn't supplying the rectifiers with AC or until the standby diesel generators have started up. If the batteries are supplying the load, then the voltage will start to decrease due to discharge. To maintain stable voltage within given limits, the battery capacity has to be correctly dimensioned with regard to backup time and the size of the load. With standby diesel generators, you can normally reduce the size of the batteries. To protect the telecom equipment against interruption of power supply, Most battery plants are designed with 2 or more batteries in parallel. By connecting several batteries in parallel, reliability can be increased substantially. Now, during maintenance, you would then be able to disconnect one battery string from the power plant and still have 1 or more batteries in operation. The battery is connected to a battery connection unit that functions like a switch or fuse in case of failure in the system. This unit can also disconnect the batteries if the voltage level drops too low to prevent them from being discharged to a lower limit than allowed. If you wish to know more about batteries and how they're handled, all you need to do is to refer to the separate film clips about batteries. In a full float system, the rectifiers are connected in parallel with the batteries and the telecommunication equipment, and a constant DC voltage is maintained to these units. In such a system, the rectifiers continuously feed the batteries so that they're kept fully charged during normal operation. In a mains failure, the rectifiers are no longer supplied with AC and thus can't rectify the AC into DC. So the telecommunication equipment will have to be powered by the batteries during mains failure. This DC feeding from the batteries starts automatically. The distribution unit distributes the current via DC distribution cables to the telecom equipment. To prevent the whole system from going down in case of a failure in the system, you'll need a distribution unit with fuses or breakers that will ensure DC distribution to the different parts of the telecom plant individually. There are a few different principles of how to distribute DC, but the 2 main methods used to distribute DC to the telecom equipment are low or high ohmic distribution. So let's now hear Harold explaining core power solutions for low and high ohmic distributions.
This cabinet is an example of the core power solution. In this particular example, we have got a bank of rectifiers which take the AC power source into the cabinet and it converts it into DC and a lower voltage. This is then combined with backup batteries, and so we can provide a nice continuous and stable DC source to power external equipment. In the event of a power failure, the DC batteries will continue to supply the external equipment. So this external source is being fed via these breakers. We have got 2 banks of batteries, power breakers, and we are feeding external equipment. However, this particular example is configured to have a low ohmic distribution. This actually is not so suitable for a switch or an exchange. To do that, we need a power distribution unit, and we have housed these in another cabinet. Here we have the power distribution units, and here you can see we've got many low current feeds with a high ohmic distribution to feed the external equipment. So let us take a little look at a switch and see how this power is actually used. In this particular switch or exchange, we see that we've got many low current DC feeds to the various units. But if one unit were to generate transients, switching transients, sending them back down the power supply, then these would not, for example, come back up here and disturb this unit. So the high ohmic distribution would remove these switching transients, and this is the basis of the core power solution.
For more information about low and high ohmic DC distributions, we'd remind you that you can also refer to the separate film clips for installation engineering. A DC load is any kind of equipment that draws power from a DC power supply system. In our case, the load consists of telecom equipment. Power and climatic systems provide the load with energy and the right operating climatic conditions. The normal operating voltage window of Ericsson telecom switching equipment is minus 40.5 volts to minus 55 volts. Normal operating voltage window for plus 24 volts RBS systems is plus 19 volts to plus 29 volts. Now, you may find that you have different types of telecom equipment on your site, and if so, they might be running on different voltages. In such cases, there are DC-DC power modules and sometimes DC-AC inverters available. DC-DC power modules convert one DC voltage to another DC voltage, and in other words, plus 24 volts to minus 48 volts, or vice versa. The modules are usually integrated with the telecom equipment. In the power distribution cables, from the battery to the load, there's always some voltage drop. This voltage drop is proportionately related to the resistance of the cable. So, if the cable is longer, the cable resistance would be higher, and consequently the voltage drop would be higher. But with a thicker power cable, both the cable resistance and the voltage drop would be lower. In order to feed the telecom load with the minimum voltage U minimum, the battery should at least generate U minimum plus voltage drop. So once again, the site engineering and correct material lists are very important in order to do a proper power installation. To be able to supervise the whole power system, you'll need some kind of supervision equipment. This is commonly called I/O device for telecom equipment, and it's normally fed with AC. Because it's important to have a backup for the I/O device as well, the power can't be supplied directly from the AC mains. To create an uninterrupted AC supply to feed this equipment, inverters or UPS are used. An inverter converts DC voltage to AC voltage. The inverters are normally fed with DC from the rectifiers. But during a mains failure, they're supplied with DC from the batteries. The main characteristics of a UPS, that's an uninterrupted power supply, are: the UPS takes the AC from the mains and transforms it into reliable and more stable AC by means of an AC-DC-AC conversion process. During this period, it also charges its own batteries. During mains failure, it pulls DC power from its battery banks and converts it to AC. Most of the power supplied to the telecom equipment dissipates as heat. So, the switching equipment and the battery banks need to be maintained within a set temperature band for optimum performance and longer life. We achieve this with the climate control system. This mainly consists of air conditioners, temperature sensors, and a control unit. Though telecom equipment can work in a wide temperature range, preferred room temperature set by operators is between 23 to 30 degrees Celsius. So that was an overview of the power systems used on telecom sites. For more information and to learn how typical power installations are performed, both in Ericsson core equipment and in RBS site, please refer to the separate installation film clips.